In this lecture, we're going to start converting that two-dimensional picture of a molecule into one that's 3 dimensions. And this can be really challenging if it's hard to visualize 3 dimensions in your mind's eye. We'll give you some tools to represent things on paper in 2 dimensions in a structured way that's supposed to represent 3 dimensions, but it definitely doesn't have the artistic flair that makes it really look that way. We can also work with online tools that'll model and allow you to rotate something in 3 dimensions. And we can work with modeling kits for chemistry that will allow us to create physical ball and stick models of molecules too, so we can turn them around in our hands. So we'll try to pair this 3-dimensional picture that we're going to draw in 2D with an understanding of something that we can like move around. So to do this translation from 2D to 3D, we have to introduce a new theory. It's called VSEPR theory. Yeah, it's a mouthful what it stands for. Valence shell electron pair repulsion theory. Blech. So basically it means that the outer electrons in an atom, or the lone pairs that are on an atom that's then bonding, all of these spaces where there's electron clouds are going to have negative charge. And as they approach other clouds of negative charge, they repel each other. So just like electrons are attracted to a nucleus through the opposite charges being attracted to each other, that electrostatic force, similarly, same charges will repel each other. And so our electrons repel each other. And that can be the electrons that are in the outer electrons of an atom. It can be the lone pair on an atom that's bonding, and those lone pairs can repel each other, but the lone pairs in the atoms can repel each other as well. And so around any central point of a molecule, there'll be these different groups of electron clouds around it from either bonded atoms or lone pairs. And the idea is that they're going to try to get as far away from each other as absolutely possible. And so all of these things that are connected to a central atom through bonds or just by being the atoms within it, the electrons within it, they're going to arrange themselves into a geometry that maximizes that distance from one another. And that makes them very predictable. We can say, oh, okay, well, if everyone's going to maximize their position so they're as far away from everything else as possible, then the number of things around the central atom will dictate like where those are relative to each other. And so we will create 3-dimensional structures from these 2D ones using this principle and just try to get everything as far away as possible. We looked at water before, and so I'm going to look at water again. So here was our Lewis dot structure. Wrong thing. Here's our Lewis dot structure for water. And you can see we have 4 different groups. We've got 2 atoms that are going to create negative charge, balls of electron density, and these lone pairs as well. And so we have 4 things that have negative charge that are going to need to be as far apart from each other as possible. So now this part's a little hard for me. I think thinking in a sphere around that oxygen atom rather than in 2 dimensions. With all that space around it, the furthest we can get 4 points away from one another is actually in a kind of pyramid shape around it, where everything is about 109.5 degrees apart. So a lot of textbooks for water will be really specific and say it's 105, and it is. But anything that's going to have this same type of geometry, we can also just say it's about 109.5, because that would be the furthest you could get things apart. The lone pairs are going to take up more space, and so that kind of crowds the atoms. But this is all just to say anything between 105 and 109 is an acceptable bond angle. So that means what we mean by bond angle here is that the angle right here between the hydrogen, let's highlight this, between the hydrogen and the oxygen and the hydrogen, this right here is about 109 to 105 degrees. And that degrees is that just like how far apart it is right here. And if we were to look at the bond angle then between a hydrogen and the oxygen and a lone pair, we would see an angle also of about 109 degrees. It might be a little bit larger, like 112, 110. But it'll be relatively even-ish around it, the atom, as these things try to give each other a lot of space. The reason that there's a slight difference here off the 109 is because these electrons that are lone pairs, they take up actually quite a bit of space because there's nothing else that they're attracted to on the other side. So they just kind of like sprawl out into these large lobes of electron density. And so we, as chemists, have naming conventions around the shape of molecules that are based on seeing where the nuclei are relative to each other. And that's because the techniques that we use to understand their shapes give us a good idea of where nuclei are relative to each other, but are not refined enough to be able to really pinpoint where electrons are, because electrons are so fast and all over the place. We can kind of get a sense of their probability of where they're going to be. We can't be like, oh yeah, that electron's right there. So we can't really map out where these lone pair electron clouds are, just where the atoms are. And so our naming conventions are just based on the atoms. And so in this case, we have a picture where we have 3 atoms in basically a triangle shape, and we would call this bent. And so this shape around the oxygen is a bent shape. And we would say it's relative to the oxygen. So the geometry around the oxygen is bent. Since this is such a small molecule and it has only one central atom, we can say the molecule's geometry is bent. And you'll see that out there in a lot of textbooks. As molecules get bigger and bigger, it's really hard to say the whole molecule has a shape. You're like, it's a blob. It's a big, old, weird blob because there's lots of atoms that have shapes around them and they all kind of add up to mess, like there isn't a specific pattern, like they don't form a nice triangle.